on together, and it is amazingly accessible for us to observe. It's the only giant eruption that we can see close enough to get a lot of these processes. And you'll see resemblances to things like quasars and a lot of other processes, some of which are genuinely unique. There really isn't anything else like it. But it's only part of the big problem, which is unfamiliar to most astronomers yet, and that is the problem of giant eruptions. Giant eruptions are a phenomenon that are totally, almost completely unexplained yet. And for that reason, even though it's a little bit divergent from the subject of this meeting, I have to spend a few minutes telling you about the problem. So let me begin with giant eruptions. Giant eruptions are extremely luminous stellar outbursts that are sometimes, or quite often, mistaken for supernova events. Some of them produce a total amount of radiative output equivalent to a genuine supernova explosion, but over a much longer period of time. Historically, Eta Carinae is the prototype, but there were several others that were seen many, many years ago. Since 2000, with the supernova surveys, there have been a whole lot of others. They usually have supernova names, but we now know they were not supernovae. Eta Carinae's light curve is shown here, and you get the idea right there in the picture. Its peak brightness, that's an absolute visual absolute magnitude, was -14. Now you see that's not nearly as bright as a supernova, except now look at the scale of years. The darn thing went for 20 or 30 years. So when you integrate the total amount of light that came out, it was fully as much light as a pretty bright supernova explosion. The other thing you can see is, what was the phrase that Gary used for Nova Cygni? A good, clean bang. This is not a good, clean bang. This is a long, remorseless, complicated outflow. And to this day, no one knows why it happened. The result, in the case of Eta Carinae, was the ejection of 20 solar masses of material and about 10 to the 50th ergs of radiation plus kinetic energy. That puts it in the supernova class, if you don't care about piddling things like neutrinos. These numbers have only been recognized in the last 20 years or so, and we think they're probably representative of giant eruptions in general. A normal supernova is propelled by a blast wave. The main point about a giant eruption is it is not. It's a continuous outflow. It's a super Eddington flow. There are photons trying to escape from an opaque outflow. They diffuse outward, and in diffusing outward, they communicate their momentum, and they push the flow. So the flow is propelled by a super Eddington, by the radiation, by the fact that it is super Eddington. By the way, that is an enormously difficult physics problem. You just try to work out sometime how to push material with radiation. If you write down the one-dimensional equations, you will be totally, absolutely, horrendously wrong. It is a fundamentally unstable three-dimensional problem. Now, there's a scale of giant eruptions, and we've only become fully aware of these in the last 10 or 15 years, but we knew of some good examples 30 years ago in addition to Eta Carinae. If it produces a luminosity of 10 to the 8th, it's probably a real supernova with a trick, and the trick is extremely important, and I'm going to tell you about in a minute. On the other hand, an extreme luminous blue variable event, Eta Carinae may have been one, is more like 10 to the 7 solar luminosities. And then there are major luminous blue variable events around 10 to the 6. I obviously don't have time here to explain what luminous blue variable stars are. So all I can really do is say, watch out about the term, because there's a lot of misunderstanding in the literature. Oops, I skipped a slide there. Or did I? The probable explanation of these events is sometimes called the LBV instability. We have some pretty good ideas of what they might be. Sometimes we call it the modified Eddington limit, and we can describe to you in hand-waving terms how that instability works. I don't have time to do it today. We have some pretty good ideas, but no one's ever been able to simulate it exactly in the modern style. The point is, when a star gets above about 1/2 the Eddington limit, it has certain unstable characteristics in its outer layers. And when certain characteristics get in that regime, it tends to explode, but in a style that we can call an eruption and not an explosion. One of the reasons we don't understand it is the amount of theoretical work has been amazingly small. Now, this was first noticed in connection with the so-called luminous blue variables. This is one of the first Hertzsprung diagrams that's appeared in this meeting, and luminous blue variable stars fall at that location. Most stars on that part of the HR diagram do not have L over M ratios within half the Eddington limit, but luminous blue variables do. They are stars that, because of their histories, have lost enough mass that they are within half of the Eddington limit, and so they do that. They cause much of the mass loss for stars with masses above 30 solar masses. This has been known for 30 years, but for historical reasons, a lot of people rediscovered it. There was a sort of collective amnesia about 15 years ago, and it was rediscovered around 2005. And now it's become quite a popular idea. Now, the really bright objects are supernovae in which this has happened. A supernova explodes and the shock wave goes out, and then when it reaches the surface of the real star, it suddenly discovers that there is an enormous envelope outside the star. The envelope was caused by one of these giant eruptions that just happened a few years earlier. When that happens, the shock wave propagating out through that envelope allows the photons to diffuse outward faster than the shock wave goes. And so you soon get into a giant eruption regime in which the photons get ahead of the shock wave and they push the material. And so you have a giant eruption rather than a supernova for a few weeks or months. Now that's odd if you think about it, because why the heck would a stellar eruption occur just before a supernova? If you think about why a core collapse supernova occurs, it makes no sense. That's not supposed to be what my talk is about, but I hope you can see why that shouldn't happen. And yet it happens a ridiculous number of times. No one knows why. But on the other hand, there are cases where they are not supernovae, and where these giant eruptions that look like supernovae leave the star open for business afterward. And the star survives, and we've known of a few of these cases. Eta Carinae is one. And those are called supernova imposters. Van Dyke originated that term back about 10 years ago. Caveat. It's very hard to learn about this subject because much of the literature is downright misleading. The supernova enthusiasts know so much about blast waves that everything they see is a blast wave. and so they can't describe this subject very well. Many people don't understand about LBVs. There's a lack of familiarity with earlier work, so it's just hard to find out much about it. Now to the main points. When you see one of these objects, there's a sort of an interesting thing about the emission lines that it produces. Generally speaking, any opaque eruption looks alike, except for its luminosity. And it works like this in terms of physics. The opacity is dominated by Thomson scattering. And so there's an outside sphere. This is an eruption going on. There's an outside sphere which has an optical depth of 1, but the photosphere, which is where the light was created that measures the temperature, is further in. That photosphere is caused by what we call the thermalization depth. If you've never seen the concept, I won't dwell on it, but the point is it involves the absorption and the interaction of the light with the material, and it usually occurs at an optical depth of about 2.5. That optical depth depends upon the density of the wind, which is categorized by the horizontal scale here. And for a wide variety of mass loss rates, it tends to settle down in the range between 10,000 and 7,000 degrees. So these things often look like they have temperatures of 7,000, 10,000, 13,000 degrees. Here, for example, is supernova 2011. And it started with a temperature like 12,000 degrees, and as it went on, look at the continuum, it settled down at about 7,000 and then dissipated. Now, do you see something funny about the shapes of those emission lines? The optical depth of the photosphere is about 2.5, and the emission line is formed outside that. That means the emission line always has a Thomson scattering optical depth of around 1 or 2. And that automatically produces Thomson scattering wings. This led the supernova people to a completely false misinterpretation. They looked at these 4,000 kilometer per second line wings and thought there were speeds like that there. With Thomson scattering wings, you don't need anything like that. The actual speeds are like 500, and they mistakenly thought there was 4,000. You don't need anything like that. So they misunderstood that. Now you can read about this literally in 5 minutes, something I talked about at a meeting in Hong Kong a few months ago, and I understand the proceedings have just appeared. So I urge you, if you're ever interested in learning about giant eruptions, this is the place to do it very quickly. Now on to Eta Carinae. Here's the picture again. And now here are the parameters of the eruption that happened. I repeat again, we do not know exactly why that eruption happened, but the star itself is the most massive star that is well established. Its initial mass was something in the range of 200 solar masses. It happens to have a companion that's somewhere around 50 solar masses. Today it's much reduced in mass, and the luminosity is around 5 million solar masses. It is in a highly eccentric orbit like that, and something strange happens near perihelion, and that's important for the emission lines I'm going to describe. Now, most of the ejecta from the event came out at about 500 kilometers a second, but weirdly, we don't know why, some of it came out at 40. And they give some beautiful emission lines that you're going to love, I hope. And some came out at 2,000, probably the initial blast from when the eruption began. Densities range, you should love this, judging from the sorts of emission lines you've been talking about. They range all the way from 10 to the 3 to 10 to the 9th atoms per cubic centimeter. And there's an extraordinary range of surface brightness. This picture is a fake. It's a composite in order to get the dynamic range to show the enormous range of surface brightness. Now there's a range of surface brightness of processes there. First, the stellar wind is different from anything else we know. Second, near it, there are some slow ejections that, well, you'll see when I talk about them, some slow material. Next, there's a place with some absolutely absurdly low ionization emission processes. Next, there are some reflection regions. Next, there are some quite different emission processes there. Next, there are some quite different emission processes there. All of these regions have fundamentally different emission line spectra. By fundamentally, I mean the processes are entirely different. Whoops, I'm having trouble with the size of them. These are ancient spectra obtained with HST 20 years ago. Look at the top here. You see the little spiky things there? Those aren't noise. Every feature, every little tiny thing in this picture is either a feature or a blend. You cannot see the noise in this spectrum. Thousands and thousands of features are not just detected, but have been classified. Now let's begin with the central star's wind. It's the densest known hot star wind. Begin with that. Now, hit it from one side with the wind from a hot star, 3,000 kilometers per second. Carves out a cavity, and there's a shock wave. The shocked region has several million degrees Kelvin, and it is thermally unstable. Meanwhile, the companion star is hot, and the primary star is not. I mean, its wind is not. And now, just for fun, you vary it because there's an eccentric orbit. So everything is changing, and you have this amazingly complex situation. The EUV vanishes at periastron because apparently, when it gets close to periastron, the wind from the primary accretes on to the secondary at such a rate that it collapses the secondary's, well, let's just say it suppresses the secondary's photosphere. And the secondary temporarily becomes a slightly cooler star. And it's no longer an O star near periastron. It's, I don't know, something like a B star. This is an old simulation of the situation. At the bottom there's the primary, at the top there's the secondary, and there are the winds, and there's the unstable shock features in there. At the bottom, there's the wind, very dense wind of the primary. At the top, the transparent wind of the secondary. Here's the shocked region, immensely complex. Here's the region of the primary star ionized by the secondary star. These are some of the earliest STIS spectra of the wind that we can see. Very complex, and this is the wind. Now, the wind mostly produces spectra that are basically iron 2. Okay, iron 2. Everybody here loves iron 2. Not very high excitation. This is nitrogen 3. The luminosity of this iron 3 line here is something like 10 to the 5 solar luminosities. It is the brightest line in the spectrum. And this comes in a spectrum that is primarily nitrogen 2. It is produced, of course, somewhere near the interface of the winds. And it has changed enormously in the last 10 years. It is produced somehow in the interface between these two lines, between those two winds. The point is, the primary star apparently has been recovering from its eruption, and it has been changing in the past 20 years at a rate much faster than it ever changed before. So the whole thing is evolving very quickly in roughly the past 20 years. And it's becoming much hotter, and all the parameters are changing. And this has led to, this isn't being consistent. One of the slides seems, oh, here we are. Exactly 2 years ago, there was a periastron passage in which we were able to detect a couple of very funny phenomena that happened. First, there's this. That is a nitrogen 2 multiplet that is produced by a fluorescence this way. The relevant levels are way up around 18.5 eV. The only way you can excite those is to absorb continuum from the secondary star. But it's not bright enough except when it's nearby. So it's a wonderful tracer of the proximity of the secondary star. Usually you don't see it. And at periastron passage before this last time in 2014, we didn't see it. Suddenly it was bright in 2014. Andrea Maynard discovered that thing, and Gary Ferland helped her figure out what it was, and we published a nice paper about it. But there's something else that's more bizarre. The helium-2 apparently can only be explained by flashes, huge, tremendously luminous flashes of extremely soft X-rays right near periastron. Apparently, those shock fronts that I showed you earlier break up. I call it discombobulation. They completely break up during periastron when they become unstable and produce a flash of helium-2 emission. And those became brighter. Meanwhile, the low emission, the low ionization is becoming fainter. You can read about this stuff in these places, which you can look up later. Now, in the inner part, of the homunculus nebula, near the star, there's a wonderful variety of emission lines that are more nebular in character. Andrea Maynard used those a few years ago to parameterize the secondary star. I'll say this very quickly. And she used cloudy to do that. Those lines are slit positions where we used HST STIS to observe the spectra of things like, for example, this is neon 3, and this is something else Gary helped her with. Usual kind of cloudy diagrams. You compare the different line ratios, and we found the parameter range in HR diagram for the secondary star. This is basically how we know about the secondary star in Eta Carinae from cloudy. But now something better. Those slow-moving things that come out of Eta Carinae at only 40 kilometers a second, less than a tenth the speed of most of the ejecta, they come out mostly in the equatorial plane. Nobody has a glimmer of an idea of why the eruption produced slow blobs coming out. Are called the Weigelt blobs because Weigelt was the guy who discovered them. They're roughly 900 astronomical units out. They have high densities. They're very slow. They were not ejected exactly in the eruption. They were ejected a little later. That makes it worse. And they produce spectra that look like this if you're foolish enough, the middle panel, if you're foolish enough to try to print them. In fact, they are thousands and thousands of known identified lines, mostly iron 2, titanium 2, nickel 2, etc. This is 0.84% of Torgel Zethson's identified line list. The point about these is, what's the excitation process? Which is your favorite excitation process? Whichever you like, it's there. The various people working on this have shown that every damn one of those is necessary. There's collisional, there's continuum and resonance radiative, everything I've listed there. And look at the bottom line. I'm rushing over this very fast, and I'm already getting a little bit behind. The bottom line is actually unique. The Weigelt blobs, in addition to having an amazing bunch of low and high excitation lines, also show a reflected spectrum of the star, and we can show the grains there are immensely large because the, what's the word for A over E? It's very neutral reflection and absorption. It's almost gray. The R value is much bigger than 3. It's bigger than 5. So the grains are gigantic. But I just told you that the main part of the spectrum is iron 2, didn't I? The iron is not strongly depleted, and yet there is enough dust to reflect the star's spectrum somewhat. Now, this is kind of reminiscent of AGN zones. You've got the basic idea of a lot of iron 2 doing a lot of interesting physical processes. Big difference here is low velocities. There are also some smaller differences, but the same basic physics is happening here, and it's right up accessible, and it is spatially resolvable. This is a case where you can actually look at it close up and see how it's looking. Now, here again is one of these, and we do have much more modern spectra. I could have shown you spectra only a year old. I'm showing you spectra many years old. Look over at the left. The Weigelt-Knott's brightest emission line that's easily detectable is around 2507 angstroms. It's Sven-Erik Johansson long ago identified it as being some obscure transitions of iron 2 from very high levels. It sticks up like a telephone pole in the middle of the Sonoran Desert. It's just very, very bright and narrow. Someone who said that the Grotrian diagram for iron 2 is horrible? See, it's not so very horrible if you just leave out all the levels that don't matter. For me, all that matters is 2507. Sven-Erik Johansson identified the 2507 line as being from a particular set of levels way, way high in iron 2, which are excited by Lyman alpha from a particular set of low-lying levels. Okay, this is nice, so what? It's just another example of resonance excitation, except that the brightness is absurd. It is really, really high, but there's more to it than that. It should be a quadruplet, all right? It should be a quadruplet. It isn't. The lines that are detected are only a doublet. The expected form should look like the top panel. The actual form looks like the bottom panel. So what we have, as Johansson noticed way back in the 1990s, is A, we have an absolutely absurdly high intensity, and B, the intensity only applies to 2 of the lines in the quadruplet. What does that? A laser does that. A natural UV laser. But you can look at the occupancy numbers for these levels. We know how bright things are in Eta Car. It falls 10 to the 7 times lower than it ought to be. The occupancy levels numbers in the levels should be only 10 to the minus 7. It doesn't make sense. Johansen and Letikoff wrote a number of papers explaining how this could work like a laser. And they are worth reading if you can. They're very complicated stuff, which I can't possibly try to explain to you in 3 minutes. One other object in astrophysics shows these possible UV laser effects. It's called AE Andromedae. It is an extremely luminous star in the Andromeda Nebula, and it also shows absurdly bright emission. Roberta discovered it many years ago, and it, well, we've tried to observe it with HST, and the TAC has consistently turned it down. Gracias. At the same time, okay, there's a big problem about Lyman alpha. The resonance that excites this line I just mentioned is not very close. It's 600 kilometers per second off. So to do the excitation that Johansen mentioned, you need to have so many scattering events that essentially the Lyman alpha, just imagine Lyman alpha scattering so many times that the natural line broadening makes it that wide, 600 kilometers a second. So you need an optical depth of about 10 to the 8. That's easily attainable in here, but it means that the Lyman alpha has to be formed inside the Weigelt blob itself. But there's a similar thing here. Oxygen, I should have written there, oxygen 18446. I bet a lot of you know that line, right? Oxygen 18446 also shows in the Weigelt knots. It's not so fiendishly bright, but it's there. The only way to excite it is by Lyman beta fluorescence. It too, well, to use Lyman beta, what happens with Lyman beta? Lyman beta gets destroyed within a few scatterings by emitting H alpha and then Lyman alpha, right? So it has to be optically thick to H alpha, and it's hard to do. You're in this situation where you have fantastically high optical depths to everything in this object. Now, there's another odd thing about the Weigelt knots. Grant Remen, an undergraduate at Minnesota, used the newest, more modern type of HST data a few years ago to measure just exactly where these lines are being produced. The vertical scale is the distance from the star of the peak of each kind of emission line. The red emission lines are boring iron 2 and titanium 2 and nickel 2 and stuff like that. The green lines are like iron 3. The blue lines are more highly excited, neon 3 and stuff like that, and the purple lines are the iron 2 2507. The more highly excited ones are coming from the outer parts of the Weigelt knots. Now, do not say shock bow wave, because there's not enough energy. There just isn't. And so we don't understand exactly how the excitation is happening. I made up a funny situation here where the excitation of the high excitation is in a sort of ablation flow, section 2 in the picture, and the low excitation is section 1 in the picture, and we're seeing it that way, and it's an illusion, but still, it's a very strange problem in the emission situation. Don't worry, I am getting near the end if I can make the, there we go. Now, further out, there's something called the strontium filament. The iron lines you see there are iron 1, and it's called the strontium filament because it's terribly bright in strontium 2. The person who is most famous in connection with this is Manuel Bautista, who's written a lot of articles about it. Apparently, in that region, the whole complex emission system is radiative excitation at very low ionization levels. It's not molecular, it is mostly atomic, but it's mostly unionized, iron 1. So in Eta Carinae, you have stuff ranging from helium-2 near the star at certain times down to iron 1. And yes, there are molecules, but I hate molecules, and my clock says 36 minutes. So molecules would take, they happen in the lobes and the ejecta, and they would take another 10 minutes. I have not done justice to this story, and many of the stories I've been telling are old. And that's because very few people have been working on them. Now, I recommend the Weigelt knots for any ambitious emission line modelers, because not only are they fascinating for the physics, but also they may have connections with the AGN stuff, and also because the physics is just plain interesting. Eta Car needs theoretical work. Also, it has a history of people writing a paper in which they say, well, we've solved this problem, and then we get new data, and I've been showing this cartoon since 1991, and the cartoon elicits an uneven response from people, because some people see the point of it instantly, and other people need about 2 minutes. Fortunately, I don't have anything else to say. That's probably a good thing.
We have time for a few questions.
Thank you. Chris, maybe I can try to provoke you a little bit. Eta Carinae is a binary system.
Right.
And the overall structure of the ejecta is bipolar.
Right.
Do you think that a binary system is necessary, sufficient, or neither for giant eruptions?
A, no one knows. B, all the theories about giant eruptions concentrate on, I'm going to get up to about G before I finish, concentrate on the proximity to the Eddington limit. C, a lot of people say that Eta Car's eruption was triggered by the companion star. When you figure out the tidal forces, you find when it comes at periastron, it gets close enough to make a significant tidal effect. But there's no way it can communicate enough energy to cause an eruption. You see, triggering is a different matter from instability. It's probably a case where it would have become unstable if you'd let it go 1,000 more years. That's just my opinion. You see the distinction between triggering and unstable. If it had just been allowed to go a little while longer, it would have had an eruption anyway. And the eruption probably happened sooner because that darn companion star stirred the thing. A lot of people speak with great confidence about this subject, and they publish papers that read very confidently. But the papers are mostly words. Yes, Gary? No, I don't mean, I'm not accusing Gary of publishing papers that are mostly words. He does not do that.
I wanted to make a sociological comment. Can you back up to the image? Probably the greatest, not the car, there we go.
Right.
It used to be in Hollywood, things blew up as 1D spheres, and then Chris did this image. And ever since then, I believe, when the Death Star in Star Wars blew up, it blew up as a perfect imitation of Eta Carinae. So your work has profoundly changed the flow of how things blow up in Hollywood. So that's probably one of the greatest contributions astronomers can make.
Thank you for mentioning that. That is precisely true, because there's more to it than that. You see the equatorial skirt? When you went to fireworks demonstrations, they progressed beyond this now. But 2 or 3 years ago, when you went to fireworks demonstrations, they had things like this. When the Death Star explodes today, it not only is bipolar, but it has a thing around the equator. By the way, there's a real interesting dynamical trick here. Many people think, oh, that's some kind of an equatorial disk. But look at it. It's rays. That's not a circular pattern. Whatever caused the explosion shot rays out. And how you do that dynamically, no one has published one bloody paper.
Are you sure it's not just an illumination effect where there's holes and the light gets out?
All I know is there are no papers about that. Yeah. In fact, you heard me complaining earlier, and you know I am simpatico with Gary about most things. Most papers about Eta Carinae are all words, not very many equations.
One
sorry.
last
Yes.
short comment or question. Bożena?
Is it possible that before this giant outburst, the primary star was also a binary star, something like algal type star, whatever, and what we now see is just settling into a single star structure?
I'm sorry, my hearing is so poor. Could someone...
I will try to repeat. Is it possible that the primary star was actually a binary, very close binary star, like an algal type?
Oh, yes, okay.
And then you see really the settling into a single star structure.
Whenever we do that, I cannot say no, but the problem is, since we have the existing secondary, it's very difficult to arrange a size scale where you can have a triple system. You know, to have a stable system, you need to have a very small separation and then a much larger distance to the third star. And in order to do what you said, the separation between the two original stars that would create the primary today would need to be very much smaller than the size of the primary star today. See, it would be just very difficult to do because of the geometrical size scales, at least if I understood what you meant. It's just a matter of geometry.
I think we have to move on, so thank you very much again.
Thank you.
And the next speaker is Ravi Sankrit, and he will tell you about photoionized gas in the presence of shocks. I will give you a notice 10 minutes before the end, so you'll still have 5 minutes to speak and 5 minutes for questions, yes?
Wait, please. Okay. All right. So first of all, I'd like to thank the organizers for giving me the opportunity to talk at this symposium to honor Gary. And I'm going to tell you about kind of few examples about photoionized gas in the presence of shocks in nebulae. And this is going to be very biographical in the sense that it's projects that I have sort of worked on. And some of the biographical details are present are completely superfluous, but they kind of hold the story together. And it's going to be a very simple and straightforward talk, I think. So in the happy world of optical nebulae, there are two flavors that we find, and that's the photoionized and the shock-heated nebulae. H2 regions and planetary nebulae are photoionized, and supernova remnants and Herbig-Haro jets are shock-excited. And I've been an inhabitant of this happy world for a long, long time, since my thesis project, which was 1998. And of course, the first thing is the Crab Nebula, one of the objects I worked on, is a supernova remnant, but it is pretty much all photoionized gas that you see there. The central part is the Synchrotron Nebula in blue. The rest of it is narrow line emission that's photoionized by the Synchrotron Nebula. So that was one of the objects that I worked on during my thesis. And the second one was M16, which all of you are familiar with. So I was working with Jeff Hester at Arizona State University, and he sent me off to get John Raymond's shock code, which of course has a photoionization component, to learn how to extract the photoionization part and to model these nebulae. And so I went, I got John's code, and then when we were talking about it, he also said, well, there's a meeting in Kentucky next year that is going to be organized by Gary, and there's going to be a lot of photoionization codes there, including Cloudy, which is the first time I'd heard of Cloudy. And then I attended the meeting, which was a fantastic experience, met a lot of people there, including Gary for the first time, and came across the website, which says, Photoionization Simulations for the Discriminating Astrophysicist. So I decided, well, let me just use Cloudy to do my work and not worry about the shock code as it was, and just plunge into the data. This was like fresh HST data with PIC2 data that was absolutely fantastic to work with. So now a little bit of a digression into the difference between photoionized regions in the simplest case and shocked regions, which of course all of you know about, but I just wanted to refresh some of the ideas. That photoionized regions are in temperature and ionization equilibrium. The transition region from neutral to ionized gas from ionized to neutral is very narrow. And so you have oxygen double plus at 10,000 Kelvin, and you have sulfur plus, which in a zone where there are not many electrons. In contrast, your standard shock, if say this is about 150, 160 kilometers per second shock, you have no temperature ionization equilibrium, and the recombination lags the cooling. And so you have partially ionized zones, which are maintained by the photons emitted close to the front. So what you have, in contrast to the photoionized case, is high ionization species like oxygen 5+. You have oxygen double plus at a higher temperature, 50,000 Kelvin, and you have sulfur plus in a region where you also have electrons, and it's quite reasonably hotter than in the photoionized case. So there are sort of three big ways in which one can distinguish shocked and photoionized gas. The oxygen-3 temperature-sensitive ratio, which is over 10 times higher in shock-heated gas. Sulfur-2 to H-alpha, which is very much stronger in shock-heated gas and has been used as a discriminant to look for supernova remnants in external galaxies, for example. And additionally, the high ionization ultraviolet lines, which are prominent in shocks with speeds greater than about 150 kilometers per second. So typically, the separation is possible. However, one of the things I should mention here is, going back to my thesis, so I was doing photoionization models of the Crab Nebula, and came across this one paper from Chris Davidson where he found very strong neon 5 emission from a couple of regions down near the edge of the crab. And I was working with photoionization models and cloudy and just couldn't reproduce this. And then I went back to the shock model that I had and then found that this high neon 5 could be very easily explained by a shock. And this was, at that time, one of the big questions was whether the Crab Nebula has any kind of shell outside of what is seen here. And so working on photoionization, I came across a shock and was able to sort of divert my attention to a whole different paper that I wrote. But here, of course, the photoionization and shock is very easily separable. And that's the point I wanted to make, because you can just go into one of the interior filaments and continue with the photoionization calculations to find out what the conditions are in the ejecta. But emission from photoionized and shock-heated gas may not always be easy to separate. And then when I was reading up for this, for this particular talk, I came across this paper by Chris on photoionization analysis of emission spectra of quasars. And I'd just like to mention that it's like an additional honor to be in the same session with Chris right after his talk, because these papers are like really fantastic to read. And just as a summary, the thing is that this goes into the ratio of high ionization lines to low ionization lines. So the carbon 4 to carbon, or the carbon 3 to carbon 4 in a sort of typical AGN or quasar spectrum is explained by photoionization with a certain ionization parameter, but that cannot explain the oxygen 6 emission. And then what is mentioned there is that the high ionization component is necessary. It could be photoionized, or it may be a shock. And so now what I want to do is sort of go back to sort of the main thread here, which is a couple of different cases where this difference between photoionization and shocks is kind of, you can't really distinguish it very easily. And these are projects, one of them which is complete and one of them which is current. I'll start with this one, which is supernova remnant 0057-7226 in the SMC, which is very in the region N66, very close to NGC 346, which is a region with many, many O stars. And this is work that I did with Charles Danforth and others using fuse data. Now you'll notice there are a couple of squares called POS1 and POS2, and those are 30 arcsecond by 30 arcsecond apertures that just happen to lie somewhere serendipitously on the supernova, position 1 on the edge of the supernova remnant, position 2 out in the SMC interstellar medium, while a narrower slit was being used to observe hot O stars in the star cluster. So there's sort of completely accidental spectra, and in those accidental spectra, in position 1, you see very strong oxygen 6 and very strong carbon 3, which is signature of shock in a supernova remnant, very standard. The star HD 5980 had been observed with fuse and earlier with STIS by Königsberger et al. And so what we had was a whole set of column densities of a lot of species that we could also predict with the shock models that kind of predicted the oxygen 6 and carbon 3. And here you have, from that same paper, Danforth et al., is a comparison of shock model predictions of different ionic species, the columns, compared to the observations against HD 5980. And there's a scaling for density, a pre-shock density here. But the key point is that the silicon-2 and the iron-2, the low density, the low ionization species were over-predicted by the shocks. That is, there was just very little observed towards those sightlines. And what we just said was that this is due to the ionization from the hot stars, that they're just maintaining this at ionization states higher than silicon-2 and iron-2. And we pretty much left it at that. We didn't really say very much more. But we presented this scenario for what was happening. You had an ionized region, and here the viewer is at the top. So the observer is at the top. And so you see, sort of the NGC 346 and the other stars, maybe HD 5980 and SK 80, just maintaining ionization, and so you don't see the low ionization species. And this is kind of a standard situation that many people have encountered in their studies, I'm sure, and it's probably very typical of massive star-forming regions. But the point I want to make is we just sort of, in our paper, just left it and didn't do very much more with those low ionization species at all. So now I want to move into sort of the main part of what I wanted to say, which is my current project. So I sort of left this happy world of optical nebulae to look at symbiotic systems, and part of the reason for this was working on Kepler's supernova remnant, which is one of those which has a circumstellar medium and probably the interaction of a binary single degenerate system, where the original system was an AGB star that was circling a white dwarf. And so I got interested in the system of AGB binaries, and was led to the symbiotic mirror R query, which is a current project. This is something that started work on several months ago with a number of collaborators. And I want to describe sort of how the same situation is going to be something we will encounter again. So R query is the nearest symbiotic system. It has an AGB star, standard AGB star, around a compact companion, and it has a jet. But one of the big questions about this star, it's an eclipsing binary, where the eclipse is at the same time as periastron. And one of the big questions is what actually drives the accretion in the jet? Because according to many of the models, the eccentricities for the orbit required are very, very extreme if you want to have Roche-Loeb overflow. Otherwise, it has to be kind of a wind overflow, and it's not clear whether what the processes are that are going to create the accretion and create the jet. So that's the key question. Now, here's a light curve of R Aquarii for the last 100 years or so. And back in the 1920 or so, the nebula was detected by Lampland around the system. And soon after that, you had eclipse, which lowered, around the 1930s, you had the eclipse, which lowered the mirror maximum significantly, but did not lower the minimum, actually raised it. So that was sort of evidence for the hot companion. And then it went along. Then you had nebular lines appear, went along for many years, and nebular lines are still detected. Then it went through a second eclipse, which is when a lot of the parameters of the binary were deduced as being a 44-year orbital period, and the eclipse and the periastron happening at the same time. This is because both the maximum and minimum went down by several orders of magnitude, and the temperature of the system changed, which implied there was a big blob of material probably in front of the mirror. And at the same time, a jet was detected. And once the jet was detected, pretty much all the interest of sort of understanding the system was to look at the jet, because it was the nearest astrophysical jet that had been detected. So let's look at the nebula. So here on the left is a recent HST WIFC 3 three-color image. The jet region is very clearly seen in the oxygen 3 in blue. All that is where the shocked jet emission takes place. And there's an outer nebula thought to be ejections from about 150 years ago and 450 years ago. Those are still not quite well understood, but it may be something like a slow nova. It's also a very dusty nebula, and although the stretch on the Herschel image in the 70 microns shows the entire nebula, it's very, very strongly peaked in the center. So we have a dusty nebula with a jet and a binary in the middle. And it was the subject of IUE observations over several years, and also radio observations that really showed there was a jet. Down on the right is a VLA 6 centimeter map, which shows the central star and this little blob to the right. And the two IUE sets of spectra, two different regions, The central one, the H2 region, as it was called, and the northeast jet. What I'd like you to notice on the spectra for the jet is that the nitrogen 5 line and the carbon 4 line, starting from May 7th, which is the lowest spectrum, May 7th, 1982, to January 2nd, 1985, in that 2.5 years, you had a strengthening of the carbon 4, strengthening of the nitrogen 5 in the jet spectrum, whereas in the H2 region spectrum, you had pretty much constant carbon 4, and the nitrogen 5 is almost pretty much absent. And based on this, and based on optical data, radio data, X-ray data, putting together a lot of different data sets, Bergerella, Fogel, and Parese, these are one of the models. Many people are modeling this. But the basic idea was that for the northeast jet in our query, you have a central photon source that preionizes the gas of a radiative shock. And this model's been held up for the jet itself. People have examined the jet at various stages, and this works. However, what this neglects is what's happening way down in the center. So for example, the 2-centimeter observations at higher resolution were compared with the 6-centimeter, and they found that this region right in the center, which is the H2 region as such, actually breaks up into two. There's the C1 and C2, where C1 is optically thick thermal emission and C2 is non-thermal emission, probably shocked. And another sort of piece that happens here is that HST FOC was used to observe this at sub-arc second resolution. They found optical knots which has corresponded to C1, which is the photoionized region or the thermal region, and C2, which is the non-thermal region, but also the appearance of new knots to the southeast, which shows that the jet is actually getting there's sort of input to the jet that's happening at times that are uncorrelated with the binary period itself. And so that's a very complex system. And this is the system that right now is the focus of my interest, and which seems to have this problem of a photoionized gas and shocked gas that are going to be there right in the center of this binary system that we need to somehow tackle. And what I've shown here is sort of illustrating again the problem with our aquarii, that there's two eccentricities that have been proposed for the orbit is 0.8, which brings the white dwarf within, very close to the mirror, so you can get the Roche-Loeb overflow perhaps, and a sort of standard accretion pattern, a standard accretion process and the jet. And the other one is a much smaller eccentricity in which things get more complicated or more difficult to explain. And one of the things is we do not know really what the central hot companion is. Based on photoionization models, people have suggested that it is a 60,000 Kelvin white dwarf. But that's something that is still to be determined. One of the reasons that this is of great interest right now is that the system is approaching periastron and eclipse. And so there's a great deal of interest in the community that studies this, and we're amongst them. So we are going to get some SOFIA data to look at the infrared diagnostics from the central source. We're going to try and get as close as we can to the central object with narrowband imaging as well as near-infrared spectra, and to see what effects on the emission lines this new periastron passage is going to have. And so I just want to make a very quick show SOFIA, just because show that it's a facility that's available for people to use, and a little aside that if you are interested, you can talk to me about that. But then what I really want to do now is just to conclude with the summary of the reason that I gave this talk, first of all, is to kind of say that very often we come across these situations where we get this complex situation of photoionization and shocks, and we don't really consider all of them as carefully as we should. And in many astronomical sources, we are able to infer the presence of these two gases, but they're not really separable. And it's either due to the geometry or it's due to the lack of angular resolution. And so what we need is a general computational tool that allows for the interpretation of all the diagnostic information available in such cases. And yesterday over dinner, I kind of heard that maybe a cloudy extension will allow us to do something and tackle star-forming regions where you have photoionized gas and shocks, and cases like our query, where you have a very compact region in binaries where you have the same. And I'd sort of like to end there and take 5 minutes. So yeah, that's enough. And so I'd like to end there and take questions. But one thing is that I would like to present this extract from the acknowledgement section of my dissertation, which is thanks to Gary for making the photoionization code cloudy publicly available and for his prompt replies to queries concerning the code. So this was a young graduate student, 1998. And I think part of the success of Cloudy and part of why it's so good is the fact that it's been so easy to not just use, but also to get help on and to get feedback on from people who created it. So thanks, Gary, and thank you, everyone.
We have time for some questions. Gary?
Well, just your last comment. Thank you very much. A beautiful talk. So Marios Hatzikos has a Space Telescope Theory grant to extend Cloudy over the next 3 years to include shocks, which is should be relatively straightforward. Then when the final direction would be to do it in higher than 1D. So there are plans.
Okay, great.
Another question?
So kind of a tangential question. So I haven't worked out the numbers, but if you were able to completely spatially resolve both components using something like the Chara optical interferometer, would that give you more of the constraints you need in order to help improve your models? Because this system's particularly bright, so it's within the magnitude range, but I'd have to work out the separation.
Yeah, so that would actually, interferometric methods are probably the best way to go. The real issue is that can you distinguish, can you really get rid of the mirror component well enough? And yeah, we're definitely thinking about that. As I said, this is like a new project, and my list of collaborators or people on the project had like these ... So anyone who can help us with interferometric stuff, yes, for sure.
Is there one last question? Okay, if not, we... There will be a short announcement.
Yes, I was just talking to some people yesterday whether there might be any interest to visit an exhibition on the campus here by an Indian sculptor called Anish Kapoor. Some of you may have heard of him. He is, in fact, very famous. I did a radio BBC program with him before I came out here, and he said, must go and see my exhibition. And I just wondered if there's enough people, we might go more or less straight after or 15 minutes after the end of the session today. And I have to take some advice from the organizers. If there's enough people, we could get one of the white vans to take us to the exhibition, and we would have to pay the driver maybe 300 between us all, which wouldn't be much to wait. And then he would take us back to the hotel after, say, 45 minutes or maybe an hour. and there's plenty of time before the conference dinner. So maybe we could just get an idea of the number of people who might be interested to do it and see if there's enough for a van load. So that's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that sounds like a good number. Sounds like a van load. So I'm not sure how to do this. Maybe come and see me and we'd get the names. The question is whether we need to buy the tickets first ahead of time or whether we need to get them at the place. I need to ask the organizers. Sorry?
We can do either, but we don't know if there are lines or queues or not.
No. Well, would it be better to get a group, get the number and then get a group ticket? Or is that possible? Well, we'll investigate this, investigate it over. Okay. Well, all right. It would be good if somebody who speaks Spanish could phone and ask. Yes, it would be very helpful. Yeah, maybe we will do that. So I would suggest you don't buy one yet, but somebody who speaks Spanish could phone, and then we'll know what to do. Thank you.
Okay, thank you. So now we have.
One last announcement, sorry. Please remember that today is the last day of the posters. The posters will have to be removed this afternoon. Thank you. It's your last opportunity.
Yes. So now we have coffee break and we resume at 10:45 sharp.
You talk
Hablo.
Ah, ok.
Hablo muy fuerte.
Ok, te presto este es el apuntador.
¿Sí?
Está más fuerte que el otro. Se va a bajar la pila a la mitad.
No me digas.
Sí, no, de este, mira, apunta.
No, son iguales.
Ahorita le cambio pilas a este y ahorita le cambio al otro.
¿Seguro? Ok, ¿el verde no hay? No, está bien. No va a dar problemas. Y tú caes, ¿no? Cada vez, ¿no?
Ok, hoy sí me sacaste una sonrisa.
No es muy fuerte. It's not that strong. You should have presented this one. You should have presented this one. You know more about the evolution of cloud than myself. But
I was money at the time.
Sorry?
I was without money at the time.
Ah, yes. So they asked me, evolution of cloud is...
Good luck.
So, gracias.
Something changed my mind. I don't know what, but maybe somebody pointed out legal application.
That's great that you are here.
Oh, wait a minute. There was a guy named
Yo hablo.
Sí, ¿qué es? ¿Un PDF? Ah, ok.
Mais oui, parce qu'en fait, il n'est même pas 45. Ah oui, oui, 2 minutes, on commence toujours 3 minutes après. Les meilleures blagues sont à la fin, donc ça passe pas.
Bon. Alors juste là, aux avance de 3 minutes et j'ai 48.
Ouais, moi j'ai 45. Si Gary est là, on y va.
Okay, so now we continue the session, and the next speaker is Christophe Morisset, who will tell us about evolution of cloudy.
Thanks, Christina. Well, first of all, I have not enough words to thank the scientific committee to give me this opportunity to present you some my view of the evolution of cloudy. It's a bit strange to talk about a code that started to be developed when I was 11 years old, and about the story of photoionization code that start when I just born. Well, but I will try to do my best anyway. So we are here to celebrate Gary Ferland and Cloudy, and most of us know that Cloudy has been developed to study this kind of guys, not the roundish things that here are polluted, contaminating the picture, but the very nice colored stuff there. So we know that Cloudy has been developed first to study H2 region or photoionized gas in more general way, novae or this kind of things. So Cloudy is able to give you a nice insight to this kind of region and also to this kind of regions that are fundamentally different on the astrophysical point of view, but they are physically almost the same. So let's back to the roots on what a photoionization code or a plasma simulation code is able to do. More or less, you need first to describe the object that you want to model. To describe the object, if it's a photoionized object, you need to describe the spectral energy distribution, the ionizing one. And that is done giving a shape, and the shape is mainly determined by effective temperature if it's a star, or an age, or on metallicity if it's a cluster of stars. And you also need to give a luminosity or the amount of ionizing photons that enter the cloud. And then you have to describe the gas, the ionized gas in most of the simulation, which is described by giving the distance between the ionizing source and the gas, and the density, which can vary along the radius, the abundances, and then you have to stop the computation at some stage, and you can define the outer radius of the nebula by saying, okay, it's recombining, but you can also let the computation going on, and then you will enter the PDR on the molecular region. And you can also add some filling and covering factors, and if you enter the PDR, you have to describe also what is the density there, and you can even add some dust at some point if you want to include this. So all this is a description of the object that you want to model. On the other side, there is a lot, but very a lot, you will see this later, of atomic data that are needed to describe all the reaction or all the things that happen in the nebula. It can be photoionization, cross-section, recombination, collision, excitation, all these transition probabilities, and also you have to set density properties and the molecular properties if you enter this. And all this is put inside the code, and the code is running and is computing, well, basically, the transfer of the radiation and some equilibrium, the ionization equilibrium, thermal equilibrium, and molecular equilibrium if you enter the molecular region. Well, basic things. And some outputs that you have from this code are the electron density, electron temperature, ionic fractions, molecules, all this in different places in the nebula, within the nebula. You have also the line emissivities, and if you integrate the line emissivities, you have the intensity that you can compare with the observation. Dust emission, if you have dust, the absorption and emission of the continuum, and you can also have, as a result of the run, the heating and cooling rates, for example. Okay. You can also run this kind of codes without describing an object, but just making some grids imponing the electron temperature. You fix the electron temperature, and you can compute what are the line emissivities given some densities or these kind of things. Okay. So basically, the art of doing photoionization models is transporting a point from a very multidimensional parameter space into another very multidimensional observational space. So the parameter space is all the input that you have to set up for the code to run, and the model is running, and then you obtain these outputs, line ratios, that you compare with the observations. You can also have some images if you have a 3D code on dust continuum, these kind of things. And so from the P space to the O space is doing a model. It's very easy, just run cloudy. Most of the time, we just want the contrary. We have the observation, and we want to know what are the abundances, what is the effective temperature of the star, or whatever describing our object. And the main problem is that in the transformation from the P space to the O space is not linear at all. And if it were linear, it would be very easy. Just make one grid and it's over and it's fine. But no, just here an illustration from a paper by Grasina and collaborators. The parameter space, a very Cartesian regular grid in metallicity and ionizing parameter. And when you transport all these points into the O space, making a grid of model, well, this is what you obtain. These are observations, O2 here, O3, and to the famous BVT diagram, for example. And you can easily see that for one position in the O space, you can have 2 or even more points in the P space. So this is where the problem is very clearly expressed, I think. Okay, so let's back to the history. And the first codes, 50 years ago now. The first one, I think, is from Chelming in '66, and Bob Rubin that developed codes for H2 region. At the same time, more or less, Goodson, Flower, Harrington developed other codes. Each one of these guys developed its own code, photoionization code at the time, to study planetary nebulae. Williams in '67 made a code for studying Crab Nebula. Also, galaxies were objects to study at that time. So in '69, Bacall, followed by a lot of people, Tarter, Davidson, McAlpine, Shields, and Netzer for QSO and Cepheid galaxies. Kirkpatrick in '70 made the first 3D model of a planetary nebula. I was very surprised to find this paper, and it's very impressive the work done with even making images of the planetary nebula in emission lines in O3, N2, and H beta lines. Very impressive. Then to study nova, Romeck-Lilenda and Shields and Ferron and Shields started to develop some code. And something very interesting, Pequignon and Stasinska in '78 used photoionization code not to determine the parameters of the object, but to play with the atomic data and to see how they can determine the charge exchange rates for a given planetary nebula, here 7027. And the first paper, led by Gary, where something that was the nucleus of cloudy was presented is in '81 for Nova DQR. This is the paper. So it was an X-ray and a model for the nebula Nova DQ Hercules. And cloudy is not named as cloudy itself, but the program that was used, this is the nucleus of what is later named cloudy. Another very important paper describing now very cloudy is this paper in '98, where the description, the full description of the code of the cloudy itself is done. And at that time, and since there, in almost all the publication, a very particular attention is paid on the atomic physics. And that's a very important point in what we are doing with cloudy. Changing the atomic physics obviously change all the results. So you have to pay very attention to the atomic physics you are using. And this was the first time that it was directly accessible with a link to the web, and the code was in Fortran at that time. And the second and last paper describing a new version of cloudy has been released 3 years ago with Gary and all the developers at that time. And it was published in the Revista Mexicana de Astronomía y Astrofísica 3 years ago, and it presented the latest version. This is the one that is still available. If you connect to the nublado.org website, you will have the C13 version. By the way, yesterday was released the latest version of the C13 cloudy code, the C13.04. So I'm impressed, very impressed to see that during its own meeting, Gary is able to publish a version of cloudy. It's incredible. So, a very short stories of cloudy. Here, the first column is the name of the version and the years. So the first version, I don't know if this is the version 0 or 1, depending if you are a C guy or a Fortran guy. Okay, the first version was in '78 when Gary was at Cambridge, and it was named a model photoionization program. And then there were some fixed versions that were released and that are still available. I downloaded all the versions to see what they look for. I had some problem to decompress some of them because they were compressed with something that is not anymore easy to find in a Mac, at least, but in Linux it was possible. So in '86, there was a very important Meudon workshop. Meudon Observatory is close to Paris, for people who don't know. And Daniel Pequignon invited all the people who at that time were developing photoionization codes to meet them together during 2 weeks, I think, and they compare the results of their photoionization codes. That's a very important thing. Stellar people should be the same, should do the same, and they never succeed to meet them together, and we just don't know why they disagree. But in this very important meeting, all the people doing code were there to make the same model, or the model of the same nebula with the same input parameters, and compare the results. And they discover some bugs, I imagine. They discover that most of the discrepancies are due to atomic data. That's very important. And some of them correct their code, and we have now an agreement. Well, after this, we reached an agreement. Or if there were a disagreement, people were knowing why, at least. Then a few versions later, Gary himself organized a second workshop, the first Lexington one in '94, where also people meet to compare their results and to see how they evolved in the last meeting. It was very interesting. So the '98 paper I just mentioned here, where cloudy is now described as a large-scale spectral synthesis code. No more photoionization, is more extended now. And at that same time, they switched from Fortran to C. There was, if you look on ADS, you can find a paper where Gary explained why and how they changed from Fortran to C. Mainly, it was to try to form people to use C to give them more opportunity on the job market if they don't follow in astronomy, for example. And it was quite a good idea because you can check that C is really more asked for computing science people than Fortran. If you stay in science, Fortran is very used. But if you go elsewhere, then you need to talk C or C++. It's with Python and Java, they are the four more asked language for computing science people. Well, the second workshop in Lexington, the third of this series of comparing code workshop, has been done in 2001 in Lexington. Then a few versions later, was the naming, the way versions are naming changed a little bit. So instead of increasing number of versions, it was related now to the year of the release directly. It's easier to see when a version is released. And so this is a paper I mentioned, the last one that described cloudy. And now cloudy is not anymore a photoionization program, nor a spectral synthesis code. It's a plasma simulation code. So you can see the evolution in the way cloudy is described by its author. So back to the old time. This was cloudy at 10, not there, but there. This was this pack of cards that were used to make code at that time. These are a picture from '88. Cloudy at 21. Cloudy was not there, but this is how the space it would take if it would have been in the form of those cards with holes inside. And from all the version of cloudy, I made this plot. Here are the years, and here are the number of lines in log, number of lines of the code. So this is the first version, 7,600 lines, Fortran, one single file with all the data inside. This was Fortran, the blue dots are the Fortran. Here are the switch to C, and here is the switch to C++. And from the C version, the data and the code were separated files. So there were .dat files and .c files. But if you sum everything together with the stars here, you have the size of the packet that you need to have to run cloudy. And it's impressive that the increasing size of cloudy is almost exponential, perfectly exponential. I don't want to know what they will have to add. If cloudy is still running into 2050, it will be a very huge code. Something very impressive also is that starting from 2000 more or less, well, the number of lines is almost constant. It's even decreasing from C to C++. I think that some optimization have been done here, or perhaps unused routines have been removed from the package. But it's quite impressive. And now cloudy today is 38, not today, but okay, now. It's to almost 200,000 lines of code, 2,500,000 lines of data, mainly coming from Chianti and from the new version Stout, I will mention later. So if you put all this line of code, if you want to have cloudy in the old form of these cards that were used in the 70s, those cards were put in some boxes with 2,000 of them. So it will be almost 2,000 boxes of 2,000 cards each. It would be more or less the size of this archive from the NASA that has been published in 17. So something else on the evolution of more general photoingestion code. So in the Muller workshop where the photoingestion code have been compared in 86, there were almost 16 photoingestion codes and other steady shocks code. And the next meeting was in 94 with 11 codes. The following one was in 201 with 8 codes. So just, that's a pity. The last code died last year. Okay, it's just to show that extrapolation is sometimes totally stupid. But it's something true here. There is less photoionization code on the market. And it's not that easy to find people that would develop a code from scratch. The last one perhaps were Barbara Colano, I think, that nobody since Barbara started to write a photoionization from nothing. And it was already 15 years old. She was there, here, and at the last workshop, presenting the first issue of the first release of Moccasin, the 3D code that she developed. But since then, no new code appear. Okay, so the next workshop will be, I don't know where, but nor when, but I'm not sure there will be more than 5 code that could be compared. Okay, we can discuss all this later. So the title of the talk is Cloudy Evolution, but it could also be named Cloudy Revolution, in the sense that a revolution, well, for some of us, perhaps, is transferring the power to the people. And what Cloudy did is transferring the modeling power to the people. And this is mainly due to the fact that Cloudy is very easy to obtain. Just click on a link and you download the packet and you enter it and you have it. But it's also because of the manual. The very good manual of Cloudy that anybody should read, and not only once, but 2 or 3 times. No, okay, this is another one by the Kentucky United Chicken editors. But the one by Gary is Hazy. I think that everybody using Cloudy, and some not using Cloudy, but interested in stellar medium, should read Hazy. And Hazy is, this is the next version, the T716. That's a good one, a big one. It's 363 pages. And some of you know that it's not the end of the story. Hazy is 3 volumes, and the second volume is 450 almost pages, and the last one, which is on physics, is the smallest one, but it's still 122 pages. So it's a package of 900 pages. And this is really what makes Cloudy unique. It's not the fact that you can download it and install it. It's the fact that you can start to make a model within a few hours. Just have a look, and there is a short version of Hazy, which is the how it's named, the short one, yeah, quick start, and you can make a model in a few minutes, and you can start to make a model within a few minutes, and it's very, very unique in not only in photoionization codes. I think in a lot of codes there is very few codes, physical code, astrophysical code, that are coming with such a detailed description on what the code is doing, all the options that are present in the code. So it's very impressive. And if there is something that you don't understand in Hazy, or even that you didn't read in Hazy, you can always ask the Yahoo discussion group. It's very active. All the developers are present, so if you ask something, you will have an answer within a few hours, and never more than a few days. So this was yesterday, and the release of the latest version was announced there. Okay, just a parenthesis here, warning. Cloudy is a physical code. It doesn't know about astrophysics, or at least not that. It's just solving equations of plasma. So that's why you can run a model of each region on a planetary nebulae, changing just a few numbers in the input files. And these are very different objects on the astrophysical point of view. So that's the way to see that it is very a physical code. So it means that if you put an astrophysically stupid input file, it will give you a model. It will not warn you that something strange is happening there. So that's just a warning for the people that take care. Cloudy will not warn you if you are making stupid models. So you have to the astrophysicist is the guy that will know if something is wrong, not Cloudy. So take care sometimes. Okay, so all of this made Cloudy very famous and very efficient. And these are the citations of one or the other one of the two papers describing Cloudy. So it's impressive, the increase. We reached a kind of plateau here, but with very good performance each year, almost 200 citations. It has been done 1 week ago, and yesterday it was 8 or more, or 9 citation more, so it's increasing. From this kind of statistics, you can have a look at the most cited papers that are citing Cloudy. It's not a proof of quality, obviously. It's just a proof that it's more cited. But okay, I will not enter in all this, but it's impressive that to see in the 5 first one, there is Curie, Shapley, Curie, Oppenheimer. Okay, the 3 Curie papers just mentioned Cloudy as in the market, there is 2 photoionization codes, Cloudy and mappings, and we will use mappings. So they are citing Cloudy, but they are now not using it. But they compare at some moment mapping and Cloudy, so it's very okay. So you can have very easily this list and see all the different use of Cloudy that have been done. With this ADS new interface, you can ask for very interesting stuff. For example, the concept cloud. You ask for all the papers that have Cloudy in capital in the abstract, and ask for the terms that are frequently found in the same abstract. And this is very the story of Cloudy. And something very interesting that Cloudy is a tool to make models, but in very good size, there is observed also lines. So most of the time, Cloudy is used to compare the model to the observations, obviously. So somebody could make a slam on this using every word of this cloud. It would be very interesting. And this is a description of Cloudy. So I will not enter in the details of the uses of Cloudy. We are here to see how people are using it 1 week long, so I will not spend too much time on this. But it's very different uses. You can make detailed photoionization model of a given object, trying to reproduce every observations. It can be line emissions, line ratios, shapes, these kind of things. You can make theoretical studies of some physical effects, heating, line transfer, these kind of things. You can make grid of models or large, very big grids of models, like we have seen from the work presented by Sebastian 2 days ago. You can even compute cooling rates and cooling functions. And this has been very useful for some of the guys there that are doing cosmology studies. So, well. And you can also even make some study of H1, for example, or iron 2, or even other atomic data. So in the few minutes I still have, I will present you. It's hard to present the almost 2,000 papers that are citing Cloudy. It's impossible. So what I chose is to look for the hazy illustration. Each hazy book has at the front cover some plots that have been done by Gary's team or by other people, but that hazy and cloudy people find interesting. So it's coming from infrared emission, for example. Here you see how the dust emission is changing when the cloud is closer to the star, so it's heated at a higher temperature, so it emits in the bluer part of the spectra. Here, this is the same here, another hazy illustration, so you see the very clear bump of the dust emission there. If you enter further in the molecular cloud, you will have the molecular emission. It's impressive, all these molecular lines that you can find. This is another example from another hazy front cover from Shaw and collaborators already 10 years ago. This is in microns, but actually in angstrom is 10,000. Here 11,000. Yes, 1,000. 1,100. This is a UV part. Yes, Lyman effect there. Okay, so you make a zoom by a factor of 10 here, by a factor of 10 here, and then a factor of 10. So this is 1 angstrom, basically, and you see all the molecular lines that are taken into account in this cloudy computation. It has not been mentioned in the hazy front cover, but you can also make PDR models. So from the molecular, I go to the PDR. The optical have been described also. And you can also go to the X-ray spectrum. This is a very short wavelength, and you can also see a lot of line emission here. Okay. These are also X-ray emission. This is the latest one, the latest front cover that will be used for the next release. And these are well, emission in the X-ray that can directly be compared to the observations applying resolving power directly in cloudy. So it will generate something that you can directly compare with the observation, giving a resolving power. So this is, for example, the default one, but you can ask for the resolving power of Chandra, for example, and directly compare to the observations. It's quite useful. Atomic data. So people say that iron, too, is a very simple atom. This is what iron, too, looks like in cloudy. So 371, not 21, 71, so even more than what we see 2 days ago. Levels have been taken into account in this paper here. You can also, as I already mentioned, have some insight on the helium-1 emissivity using cloudy. By the way, the next version of cloudy, and this is a very good, very important, and for me at least, improvement, there will be a new format for the atomic data for the next version of cloudy. It will be one single format for almost every ions. And the Stout is the name of this atomic database. It's a kind of a la Chianti, but it's not exactly Chianti. And it will be then very easy, it will be NASCII, so very easy to change the atomic data. So if you want to change the atomic data used by cloudy, it will be very easy, just changing an ASCII file into another one. So you will be able to explore what are the effects of new atomic data or old atomic data on the result of simulation. Okay, and then another way to use cloudy is as a part of a more general code that, for example, can compute 3D, pseudo 3D models. An example in one of the front page of cloudy. It was done by Cloudy 3D. It was an IDL version of the more recently developed PyCloudy that you can download also. Well, okay. So the evolution of cloudy is very large scale. It was first a pure photoionization model, then dust, PDR, and X-rays have been added. High and low electron temperature, very extreme values have been included. High electron density also. So one of the latest slides. Oh, I have time. But okay, I prefer to have a lot of questions, and the game is that I will not answer the question, but Gary will. So that's fine. One of the evolution I saw also in cloudy is the way that people are fighting with compilers. a lot of the discussion in the developing group is due to compiler updates. The compilers are changing because processors are changing, and compilers are very close to the processors. A new compiler, if you want a code to be very efficient, you have to take advantage of all the options that make things faster. But when a compiler updates, well, sometimes the code is not running anymore. So some of the issues in cloudy development are coming from problems due to compilers. As computer became more powerful and with all this multi-CPU computer, cloudy looks like grid and optimizer to have this capacity to run multiple models at the same time on one machine. So you can have a grid of models easily, and the next version will improve a little more this possibility. And the next improvements perhaps may be achieved using GPU. I mean, graphic card processors. And that would be a way to have a faster model. Okay. So the next release that will issue, that's one of the questions. I don't know when, in a few months, I think. Or they have to rename it C17. Has been mainly developed by Gary, obviously, Robin Wias, Piet Van Hoof, Marius, and Fran, they are all here in this room. Atomic data are in a more versatile format. I told you the start format. Much more emission lines will be available, and it will be also faster. Okay. Well, the last slide will be on the next version, the next release of Cloudy. So the 22 one perhaps will offer this parallel processing. Some of the things that Cloudy itself, not different runs, but in one run, could be parallelized perhaps. And using CPU and GPU. Gary mentioned me that they are working on 3D geometry, ray tracing, for example. Ali radiative transfer is something very complicated, but very well studied also is what people making a stellar atmosphere model are using. And there are a lot of documentation on this, so we can, they can perhaps include this in the next versions. Perhaps have a look at the way to include shocks. It would be interesting to compare the results then with mappings, which is a photoionization on shock code developed by Mike and Luke. Luke here and Mike in Australia. And Will Henny perhaps could have some comments on his try to put some hydro into Cloudy or to put Cloudy into some hydro code. I don't know in which direction you are going. And so that is for my part. Question mostly to Gary, I think.
Christophe, as a computer-savvy person, what would your opinion be on this, recoding of Cloudy from Fortran to C++? What would your opinion be on that?
Well, I don't speak C, and I forgot all my Fortran almost. So since I went to IDL, and the idea, the three main ideas for which Cloudy has been transformed from Fortran to C, which I read from the paper directly, was for this market, for the students that are working on Cloudy and who will not find a job in astronomy. We know that the market is very closed, so they will have a knowledge of language that is widely used in the market. So, but also at that time, the Fortran compiler was not that easy to find. The Mac, for example, the Mac Fortran compiler from Intel is still, you have to pay to have it. It's under license. And the Fortran free compiler for Mac, the G95 or G Fortran, was not available at that time. So it was not that easy to find a good compiler that were close to the processor. efficient to make a code running fast. This has changed since there. Now the G Fortran is very efficient. So perhaps the decision would have been different if you would have to redo the same thing now. You would do it again?
I think it's the right,
yeah?
the right answer, I think.
Okay.
At the University
but,
of Minnesota, the computer science department stopped teaching courses in Fortran a long, long time ago.
Yeah.
Fortran does not exist.
No, Moccasin is Fortran 90 and is very efficient. Well, Fortran 90 and Fortran 95 are very efficient, are solving some of the issues that Fortran 77 had. So it's not dead at all. People are working with Fortran. It's not that true. But for example, some of the spirit of C has been translated to Java or to Python, the starting at zero, tables, this kind of things. So speaking C makes things easier when you are using this language, or starting from this language makes things easier when you want to learn C, for example. So, well, that was the point.
Besides, C is civilized.
Fortran?
C is civilized.
Yes, but the F for Fortran should be for what?
Beethoven wrote his first symphony in C.
Question here.
Yeah, so this is to do with you said that like Cloudy doesn't give any warnings when you put in parameters that are not astrophysically correct, but
no,
I actually remember that there are warnings if you're making gross errors. Is that not true anymore?
No, there are warnings, but it's more physical warnings. It's barely astrophysical warnings. If you make a model of an old planetary nebula with a shell very far away from the star, but very dense, it's not astrophysical. It's dense when it's close to the nebula and it expands, so the density is decreasing with the time. So you cannot have a planetary nebula with a very huge distance between the shell and the star and very dense. No, and that Cloudy will not warn about this. It will warn if some strange things are happening, and there are different class of warning, and I warn everybody to look for the warning at the output file. It's something very important. Most of the time, the output file is not that big, so people, well, okay, I will not have a look at it. Yes, there is very important things in a warning that Cloudy are issuing, but not very astrophysical in the sense I described, for example.
Okay, a question here.
I can see a pernicious effect for students, though, in all the complications. I've always had a theory that everyone learning to drive a car should be forced to begin with a 1200cc Volkswagen. Those of you who know what that kind of car is will know what I mean. If you give a student all this complicated stuff, they'll never learn what the fundamental processes are, and so they'll just run it blindly. You know what I mean? You do know what I mean. I'm sure you do. And they'll never learn the real physics. They'll just do black body stuff. And I've seen it happening with, frankly, the majority of grad students at my institution. I don't know how to fight it, but all people in senior positions using Cloudy should be aware of it. I would suggest a learner's version of Cloudy, a simplified kind of thing.
Learner's permit?
That's right. I mean it. I'm serious.
It will be even worse with those big database of photoionization models that some people are making now.
Okay.
People will not even run Cloudy. They will just download the results of the database. I know.
Okay, I think we have to move on. I just want to add a comment about the fact that you said that after Barbara Zerkolanos there were no more photoionization codes, but that's not exactly true. Actually, there is a lot of photoionization codes which are much simpler and which are merged with some hydrodynamical codes and things like that. And there is a lot of things which are not publicized as photoionization codes, okay. But we do a lot of the things, of course, in a simplified manner. But I think this is also the way things go if you are more interested in hydrodynamics.
Yeah, using cooling function instead of
not only that,
yeah.
no, ionization, there is a lot of codes like that.
Okay.
Okay, so the next speaker is Robin Williams, and he will tell about modeling material state in cloudy. Robin, I will notify 20 minutes.
Magic. And is that a pointer? So, I guess I'm going to probably start by saying. So going to start by saying various things this talk is not, and then we'll see whether there's anything left in the intersection. For a start, there's British Crown-owned copyright here. Probably about the only Crown-owned copyright thing is the logo on the pages. So. It is a large team effort. People are involved. The people are welcome. The long-term developers now are Peter, Robin, Marius, and Fran have joined on. Nick Abel is here. He did a PhD thesis. Gargi Shah did a PhD thesis on molecular hydrogen. I have sent her an email. I am very confident that this artist, you're going to go see the sculpture this afternoon, is her father. Because I don't understand quite how names transpose in India, but I know that I have a sculpture that she gave me from him. So a lot of young people have helped us. It's been a tremendous ride. But Robin has taken the lead in the numerics and the numerical methods that are being used. So it's been a big effort.
Any other comments? Yes.
I could probably just shout. The word legacy issues appeared quite a lot. Unlike, say, an operating system or something like that, I don't see why you can't just preserve, say, a particular issue, a particular model of cloudy, a simplified version that can't simply be used forever. Right? An easier to use version for simplified use.
I guess the two things. A, it requires some effort in principle to support, because as languages and compilers develop, there tends to be, I guess it tends to be decreasingly much. I guess it's also trying to ask somebody to run a model that isn't actually something that you'd feel is the best thing that they could do. Saying, well, yeah, this is probably good. This is probably good enough, rather than this is the best science you can do. It's a difficult balance to raise, of saying, yeah, okay, this is cloudy light. How do you publish a result with cloudy light?
Well, but maybe I'm not trying to publish results. Maybe I just want to explore.
So yeah, there's
hypothesis.
And I guess also particularly as with the infrastructure changes in calculations is something where actually codes that haven't been developed may actually start to get slower, start to get more problematic with, start to get more difficult to take longer to run. So then you end up wanting to make more infrastructure changes to the code. So, but yeah, it's an interesting idea to have a light version.
Yeah. Okay. I'm just saying that my age learning curves become much more acute.
Yeah.
I'm afraid we have to move on. So we'll thank our speaker again. And the next talk is by Thomas Haworth, who will tell us about 3D radiative transfer. I'll make a notice after 20 minutes.
Great, thank you. So my talk is still on 3D photoionization and PDR modeling and hydrodynamics as well. But I've changed the title to Torus and Torus 3D PDR, just because this is the name of the tool that I actually use to do this modeling. So not cloudy. So this is quite a code-oriented talk. So before I started, I just wanted to point out what I'm interested in astrophysically, which is sort of split reasonably evenly between star-forming regions, so things like bright ring clouds and feedback, and also now protoplanetary disks, so modeling their structure, their dynamical interactions, and in particular linked with what I was doing on H2 regions in the past, their photoevaporation as well, so systems where radiation and matter interact. So yeah, in terms of astrophysics, this is the kind of stuff I'm doing. Now I was delighted when I got this talk. I've never been to Mexico City before, and there's also, when I look at the attendees list, loads of people here I've never met before, which is exactly what you want from a conference. But then I looked at the session that my talk had come under, at least originally, and saw that it was extending cloudy, and I all of a sudden got very nervous to come to a room basically that's going to be filled with cloudy users and developers and tell them about a different code. So I thought I'd start off by actually just trying to emphasize that although Torus and Cloudy will do some things that are quite similar, they are also very different in many respects as well. And as we've already heard, one real big way in which they're different is that Cloudy is incredibly user-friendly in sort of an unprecedented way, I'd say, which is why the code paper is getting this sort of order 200 citations a year, because people can just pick it up and use it. Whereas conversely, Torus is developed by the users are the developers pretty much. So last year we published about 10 papers, and that was a nice year for us. And yeah, I just wanted to highlight that we are interested in similar problems, people working with Torus and Cloudy, but I think our approaches are hopefully only complementary to each other. And for no moment am I going to stand here and tell you how you should be developing Cloudy in the future. So Torus 3D PDR is the code, essentially, that can do the PDR and photoionization modeling in 3D, but it is a coupling of two other codes. So the logical way to give this talk is to discuss these in isolation, and then this stuff just pops out at the end. So I'll start off with Torus. It was originated, so Tim Harries developed the code originally back in about 2000. The code today resembles nothing like what he developed originally. But he still is the primary developer, and so most of the other developers are also in Exeter as well, where he's based. And I did my PhD with him, which is where I fit in. And what Torus is, first and foremost, is a Monte Carlo radiative transfer code. So Moccasin was mentioned already. Torus is very similar. And because what Monte Carlo radiative transfer is quite important for later parts of this talk, I thought I'd just illustrate it with an example. So what we have is an ionizing source, or a photon source. In this case, it's a sun god. And assuming enough sacrifices are received, this will be emitting photons into this medium out here. And discretize the medium with a grid. And if you pull out your copy of Osterbrock and Furland, you'll see that if you want to know the ionization state of some part of this grid, at least in this simple example, you need to know the mean intensity there. So this is solving ionization balance. So what you do in a Monte Carlo photoionization code is notice that this mean intensity is related to the energy density. And what you do is you break the emission spectrum, or the energy output from this source, into small packets. Right? So bundles of photons that have some fixed energy. And the frequency of that packet of photons is just set by it's sampled randomly from the spectrum of the source. You then emit that packet in a random direction with that random frequency, and it propagates for some distance until it's absorbed. And it'll then be re-emitted and maybe scatter, and eventually will escape the system. So basically, this packet of energy evolves just like a real photon, undergoing a random walk through the grid. Now, what you're doing when you do this is, let's say when my photon propagates through this cell, it's basically a bundle of energy that exists in that cell for a certain amount of time, right? So it's contributing to the energy density in that cell. So by propagating millions of these photons and building up a series of trajectories through a cell, you can build up a picture of this quantity, of the energy density in a cell, right? So this quantity in terms of Monte Carlo estimators can be expressed like this. So this is the energy of a given packet of photons. This V is the volume of a cell. And all you're doing is counting path lengths through a cell to work out the energy density. And that can allow you to solve the ionization balance. So that's it in a nutshell. And there's some advantages to this. It works in 3D easily, as easily as 1D. And it can be in complicated geometries as well, because the photons just evolve like they would naturally in a real system. And for that same reason, you can also trivially include the process radiation field, so the photons, not just from the star, but the ones that you get when electrons recombine with ions. You can treat multiple radiation sources easily. You don't have to do anything other than sample them from more than one star. And it also scales really efficiently, because all you're doing is counting paths through a cell, and they're all independent events. So if you're propagating 1 million photons, in principle, you could run it on 1 million cores at the same time. And that's very important for some of the dynamical stuff I'll talk about. So yeah, Torus does that sort of thing. And yeah, an example of a photoionization calculation that I'm going to present is from the first meeting in Lexington. It's one particular benchmark that was developed there, where you've got a 40,000 Kelvin star at the origin, and in the benchmark you work out the temperature as a function of distance and also the ionization states of a whole bunch of species. And yeah, I have actually run cloudy models, despite the fact I'm not a regular user. In my first paper in 2012, we compared directly against cloudy to check we were doing okay here. But what I also did in my PhD was include hydrodynamics in torus and work on the coupling with the photoionization. So what you can then do is, given this is hot in the H2 region and cold outside, and it's a flat density distribution, is watch this thing evolve over time. So there's been mentions of including dynamics in cloudy. We're doing this kind of stuff. And so this is not necessarily an approximate treatment of the temperature here, like some hydrocodes do. We're explicitly computing the ionization state at each time step. And this is cool because you can look at the effects of microphysics on these dynamical applications. So in a paper in 2015, I basically just switched on and off various bits of microphysics in these sort of simple expanding H2 regions to see what was dynamically important. And yeah, you can also, you get for free basically your favorite synthetic observations. This is completely unphysical movie, really. The color scale probably changes, but I'm just illustrating that you can watch these kind of things expand. It also works in 3D. So Ahmad Ali at Exeter is modeling turbulent star-forming regions. There's embedded sources here. And yeah, same thing, just in 3D. H2 regions expanding. The red here denotes the ionization front. And so again, you can probe things like the effect of microphysics on the dynamics. As well as solving the ionization, you can also solve for the radiation pressure using these Monte Carlo estimators. So again, the energy, just path lengths and the opacity you need, and it's a vector this time. And radiation pressure is important, for example, when you're forming a massive star. Early on in its life, radiation pressure will drive bipolar outflows, and so this is being modeled here. A star will form and outflows will be driven out. And on the left here, we have the evolution of synthetic observables of this system, so the SEDs and various infrared fluxes evolving over time as the star forms and blows out these cavities. There's two just for different viewing angles. And it does a bunch of other stuff too that I don't really have time to talk about, but things like molecular line transfer, so it can solve level populations of molecules and generate data cubes and things like that. You can do co-moving frame radiation transport, non-equilibrium radiative transfer, and in the Hydra you can also include sync particles and do M-body physics. So it all sounds good, I hope. You can have, basically, one of the big pros is you can have the features of a dedicated radiation transport code in radiation hydrodynamic applications, which I don't think many people can do. And you can also get all your usual things like synthetic observations that you get from a radiation transfer code. But the price you pay for this is that it's slow or expensive. And these are sort of exclusive here potentially with the Monte Carlo radiative transfer because it does scale very well. You can run it actually quite quickly in human terms. So for example, that simulation of the massive star forming with the outflows being driven, in that, Tim was telling me that the radiation transport's taking less time than the Hydro now, just because he's running it on hundreds of cores. But yeah, our Hydro scheme also isn't that good. And yeah, the other negatives of Torus in comparison to other codes is that our photoionization is much more simplified than Cloudy, for example. There's not things like we don't even include iron in there. There's no nickel or any other heavy metals. It sort of is photoionization equivalent to a much older version of Cloudy. There's also no proper treatment of X-rays, so no inner shell ionizations, for example. So it's good for H2 regions, but not for AGN and things like that, or supernovae. So that's Torus in a nutshell. So what about 3D PDR? So this is another UK-based code, a UCL in London. And the primary carer of this code is Thomas Bisbas, who's now in Florida. And And we heard a lot about PDRs yesterday, but I thought I'd better recap. Basically, we have some radiation field coming in from the right in this diagram, and where the UV field's strong, your gas is ionized. Where you're completely optically thick to the UV, you're basically molecular. And in the transition between the two, basically, your UV field's attenuating, and your ions become atoms, and you eventually start getting molecules form as the radiation gets weaker and weaker. And we've heard all this pretty much. But an important point is that for the temperature in this region, line cooling is really important, right? And in this 1D schematic, I'll come on to 1D in a moment. But in 3D, in order to estimate the line cooling, well, the escape probability of a line photon in this direction is going to be different to the escape probability in this direction and this direction and this direction. Essentially, you care about the direction in every single direction from every single point in your simulation if you want to work out your escape probabilities accurately. And for this reason, most PDR codes are 1D. You have, not always, but sometimes just a beam of light. I know cloudy accounts for geometric dilution. And then there's some slab of material. And you assume that exciting radiation comes in, cooling radiation goes out, and everything's optically thick in all these directions. And so 3D PDR was developed to allow you to move to 3D. And the way it estimates the escape probabilities is that from this point, it uses a Heelpick scheme to break 4 pi steradians into smaller subsets, which it does some averaging over, that I don't have time to really go into, unfortunately. Yeah, Heelpicks is a fairly famous scheme for sampling 4 pi steradians. And although this approach that they've developed works, it's no sort of silver bullet for doing studies because it's just really expensive. That you could have done this sort of thing a long time ago in principle, but only now we're getting the resources to actually run this kind of thing. Because it's both computationally expensive in terms of the time to run the thing, but also in terms of memory. So 3D PDR uses the UMIS network. It can use the whole thing, but for everything I'm going to talk about today, we're using a reduced version with 33 species and about 330 reactions. And this is just a summary of what's in that reduced network. So reduced is good enough for me because it gives you temperatures to within about 10% of what you'd get from the full. And I'm mostly interested in dynamical applications. So in his code paper, where he presented torus 3D PDR, Thomas showed some examples. For example, a sphere being irradiated by a planar field. And he computed the abundances and the temperature. This is the temperature distribution. And here are some emission maps. So carbon 2, O1, C1, and CO1 to 0. So it's sort of behaving roughly as you'd hope. Your more excited lines you're finding over here where it's hotter, and you're finding your CO emission in the nicely shielded regions over here. But they then go on to apply this technique to simulations like this one from stellar Offner. So we have a turbulent medium evolving in which stars are forming, right? And although the 3D PDR approach of estimating your escape probabilities with this Heelpick scheme still applies, what do you do for the exciting UV field here? In the sphere that they modeled, they just assumed some planar field. And actually, in the paper where they post-processed these models, they assumed an isotropic field. Well, there's a bunch of embedded sources here and a complex medium. The UV field doing the exciting of the PDR is probably not going to be that isotropic. So what do? Enter torus 3D PDR, which we worked on when I should have been running my thesis. It was a more appealing thing to do, which makes writing a thesis seem really boring. So basically, the idea is if we go back to this picture we had at the start of propagating photon packets to estimate the mean intensity or the energy density, well, all the drain field really is, or your UV field that you care about for the PDR calculation, is an integral over some wavelength regime of this. Or I'm sorry that I've changed notation here from frequency to wavelength, but that's all it is, right? And so you essentially get it for free when you're doing this. You're already computing it when you're doing your photoionization calculation. Right? So just to prove that it works, we took a star and stuck it in a spherically symmetrical medium. And we know what its UV field is that it's emitting. It's somewhere up here. Now, if the UV field was just suffering geometric dilution, then you'd get this fall off in the UV field as a function of distance. But we know that we prescribe some simple opacity in this system, in which case you should get the blue line, which you basically can't see because these red Monte Carlo estimators are sitting right over the top of it. So it works. And in principle, what you want to do with this approach is if you have some complex medium like this with multiple embedded sources, you do your Monte Carlo radiative transfer, your photon packets move through the grid. It solves the ionization state, but at the same time, your photon packets are also going through this region of the grid as well, and building up a picture of the UV field there, which you can then feed into the PDR part of the calculation. And an important point to highlight is that this is really a new code in a sense. We're not running something with Torus, dumping the output, reading it into 3D PDR and running something else. We've ripped the guts, the bits that do all the working out and everything important out of 3D PDR, and implemented it in Torus. So everything takes place on the grid that Torus would use. So you can run everything in one calculation, basically. And as I'll come on to, this is also important because it allows you to do things like radiation hydrodynamics with the PDR chemistry in there. So I already mentioned the Lexington benchmark earlier. There's a star at 0 in a uniform medium, or one of the Lexington benchmarks. Well, without the PDR physics, basically you go from 10,000 Kelvin down to 10 Kelvin at the ionization front. But with the PDR physics, it drops down to more like 100, and you get a much more gradual decline in the temperature over quite a long distance, much bigger than the size of the H2 region. And so the black line here is what we computed with Torus. The crosses here are Moccasin just doing an ionization-only calculation. And interestingly, there's two other lines here. So these are what you get if you take the UV field at this point, worked out with the Monte Carlo estimators, and feed it into a normal PDR code. And if your PDR code assumes that the radiation's a beam, so not suffering geometric dilution, you get this blue line. But when you account for the geometric effects, which are automatically computed with the Monte Carlo, you get the red line, which is a much better agreement. And there's temperature differences here of sort of 50%. So even in this simple 1D test case, or illustrative case, there's already 3D considerations at least already seeming important. So we did run some 3D models. Unfortunately, they're not very interesting. And the reason we haven't done anything more interesting is because this stuff is really expensive to do. So you better have a good reason to run a model if you're going to do it. And so when we first presented the algorithm, we just irradiated some ellipses with various source configurations. So S1, we had a star with just the on-the-spot approximation. So photons only from the star are included. So the second they're absorbed, you stop their propagation. We then had a second star where we also included the random walk. And then we did a third scenario with two sources who should sum to be the same luminosity as the single one. And yeah, just seeing what the effect of the geometric effect on the PDR was in here in this ellipse. And I'm really not actually going to talk about it in that much detail. I'm just going to illustrate, just show you one example. So this is the temperature for one of the single source models. You've got this PDR. Well, out here it's about 10,000 Kelvin. I don't know if you can see. There's a shadowed region at tens, sort of hundreds of Kelvin gas here, and about 10 Kelvin in the dense gas here. This is the molecular hydrogen abundance, atomic hydrogen, ionized carbon, atomic carbon, and there's more panels if you want to keep going. But yeah, and emissivity for C1 there. So it does stuff in 3D again that sort of looks sensible. Oops. But the problems with this are that predominantly that it's really expensive. Cheers. And although the Monte Carlo stuff is expensive, at least that scales well. You can run it on tons of cores. This stuff doesn't scale very well yet. But the yet is important. It's mostly because I haven't gotten around to it. And the other thing is it's young and not very user-friendly. So it's the polar opposite of cloudy at the minute in a sense, because no one would want to pick it up and use it. So just in the last few minutes, I wanted to talk a little bit about astrophysics, actually, and just give a first real application of torus 3D PDR. So most of you, in fact, all of us this week have seen some stuff about proplids in H2 regions. So these are disks which are near O stars, and they're being irradiated and stripped of material and warped into these teardrop-like shapes. Well, these are typically really close to O stars, but there's growing evidence that disks can be affected by much weaker radiation fields, so the kind you just find by being in a cluster, not necessarily near an O star. And a sort of striking example of this is the recent observations by Serena Kim of proplids near a B star. Now, I know a B star is still big, but it's much weaker than an O star, and the radiation field it's emitting is much lower energy. So these are irradiated by about 3,000 Habbing field, 3,000 G naught. And if you want to model these, it's really hard because you need to. The FUV field is important, so the PDR physics is important. And for that reason, if you want to understand what's going on, it's only ever been possible in the past to look at the problem semi-analytically. So for example, Adams in 2004, what they would do is they would say, oh, I've got a disk here. So this is number density, radius, radiation field coming in from this direction. And what Adams would do would say, oh, I know what the conditions are at my disk outer edge. Let's just solve the continuity equations out from there and use a temperature that's from like a PDR lookup table that's pre-computed. And Fachini did something similar, but by identifying some critical point in the flow itself. And they do get slightly different answers. But the point is that these semi-analytic models, although they give you something to work with, are confined to certain subsets of the possible parameter space. And they also only work in 1D. And you also can't look at the time evolution of the thing. So what we can now do with torus 3D PDR is just set up a disk, have a cold start, and just watch the thing evolve. Oops, is that going to run? Yeah, and reassuringly, we do seem to be reproducing the semi-analytic model, which is given by these crosses. This is Fachini's model. So this is actually a really boring application again. I'm sorry that most of them seem to have been. But the point is now we are in a position where we know this stuff works, and we can really start probing the wider parameter space and looking at problems that you previously could not with semi-analytic models alone. And it's also worth bearing in mind that beneath this 1D plot, this 1D movie, there are those 33 species evolving, and this is just 5 of them. So we're tracking the evolution of, so this is the HH2 transition, the CO and atomic and ionized carbon. We're tracking all that stuff as the dynamical model evolves. Okay, so to summarize, torus 3D PDR is a 3D Monte Carlo edited transfer code with hydro and PDR chemistry too. So it can do a load of stuff. And in particular, I'm interested in looking at the impact of including reasonable microphysics in dynamical models. But it is really expensive. And in particular, if you want to do the PDR stuff, it's you're very limited at present in what you can do. But I do know how we can fix this a bit, and I'm working on it. And so I'd encourage you to go and look at maybe the things we've already done and keep an eye out for what we're going to do. And to the developers of Cloudy, if there are any bits that you are working on and maybe want to hear what's been a pain for me in maybe 3D or including the dynamics and this kind of stuff, then I'm happy to talk for the remainder of the meeting and by email in the future too. Okay, thank you.
Gary.
I thought it was a beautiful talk, and this is certainly the direction in which we're headed. You're way ahead of us in a lot of these details. I had a couple of questions about, well, first about how the Monte Carlo works. How do you do the multi-level atom? For instance, the CO rotation ladder, you have to do multi-line coupled RT.
Yeah. So actually, the the molecular stuff is currently completely embedded within the. It's actually not using Monte Carlo. It's just doing it separately using the stuff that was already in 3D PDR. So the solver for that is not actually. It maybe is a bit misleading. Is not actually done with the Monte Carlo bit. All that you get. All that the Monte Carlo does is give you the UV field, and then it's down to the PDR code that already has all these modules to do it, to solve for the CO.
The second big question I had is that the Lexington H2 region didn't have any dust in it because a lot of codes didn't have dust. So what's supporting the PDR temperature if it's not dust ionization?
Well, that was just a toy example, really. So that's a very good point. Yeah, we just took a model that we already knew existed. And again, it's sort of one thing we have to do is try and define some boundary between where the gas is photoionized, and we should do the photoionized part of the calculation, and where it becomes PDR. They're not properly, at the interface, not fully properly integrated just yet. So in that model, there would have been dust in the PDR region. But again, that's a parameter you can set. That was just an illustrative example.
Then the last thing, when the radiation comes in, if it's a drained field, that's an isotropic field. So in a beamed field, if you had an O star right next to the PDR, the beam going in would be E minus tau, but if it's an isotropic field, I think it becomes E1 minus tau. So you're doing that, the beam versus a diffuse radiation field coming in.
Yeah, so in that Lexington benchmark plot. So basically,
that was a star coming in.
Yeah, so there's with the Monte Carlo, actually, the photons in a 1D model still propagate in 3D space. You just map them back onto your 1D grid. So when they were out in the PDR working out the UV field, you were naturally accounting for that geometric dilution anyway.
And because it depends how far away the star is, though. I mean, the Tienes-Hollenbach, sort of the Tienes-Hollenbach Orion PDR was pretty far away from the star, so it's playing parallel.
Well, the photons are propagated from the star originally. So it uses detailed balance. So the photons start at the star, they move until they're absorbed, and they're instantly re-emitted with some other frequency appropriate to the emissivity of that region. And then they continue on their random walk. So the photons that reach the PDR have come through the H2 region. And they do that in 3D space, which is why you sort of naturally account for the geometric dilution.
Okay, thank you. Very nice.
Thank you. Any other questions or comments? Was there enough?
So actually, do you plan to extend this to AGNs?
Well, so the thing with this is that, as I said, Thomas and I sort of sat down and did it. It was supposed to happen with Moccasin, actually, but I just happened to be there when they were talking about doing it. And so it was the two of us who just sat in an office for a month and a half and just did it. And now I'm pretty much the only person who can use it as well, which is not good. So there is a big list of things to do, and AGN is quite far down the list. But eventually we do want to improve the photoionization. It's definitely not perfect. It's not great at the minute. It's sort of like Cloudy was probably a decade ago or more.
Any other comment or question? Okay, if not, we thank our speaker again. And we have lunch, and we resume at 2 o'clock.
Ya ves que estas compus de repente no se hablan con... Sí, ya me pasó. Está bien.